This afternoon, we're going to start working on least squares. And I know it's a bit of a downer for you to work again on least squares. You've seen that in second years. But the thing is, least square is really fundamental to machine learning. Okay? It's a first technique that was invented in terms of machine learning. So it is important for you to realize that even so deep learning is amazing, there is a wealth of techniques maybe you should consider before even going into deep learning. As I said in the first lecture, deep learning really shined when faced with hundreds of thousands of data samples. Okay? So before that, other techniques such as support vector machines or SVM were actually more efficient than deep learning. Okay? So it's only when we started to really have a lot of data that people started to realize that actually deep learning was that interesting. But when the scale of your problem is small enough, you should look first at least squares, because least squares can get you a very long way and much quicker than deep learning would for you. So how do we start in machine learning? Well, we start with data. Okay? So you've somehow collected a lot of data, and so in this graph here, you collected the heights and the weights of people. And the first thing you have to do is to graph that. Okay, so I would say the first advice in machine learning is graph your data. Just check, play with your data, look what's going on in your data. Don't jump into the equations. First, look at the data. Okay, and here we see, well, it's probably kind of a line almost. So we want to fit a line to that data, and for that purpose, we'll try to use linear regression. Okay, so that's kind of how we start. You visualize the data and you see there's something interesting in the data, and that's the kind of line we want to express. Okay, so what is this line? Well, if you reuse the machine learning terminology, we say here we're doing a prediction. Okay, so what we want to find is a formula, so here a linear equation, that will predict what the weight is given the heights. So we collected for a lot of people the heights and the weights, and now the question is, well, if you only have access to the heights information, what is the best guess you can do at the weights? And in this case, you have this formula that can help you. Okay, so I'm going to switch somehow to the. I'm just going to talk a bit about notations. Okay, and that's something that will stay true throughout the rest of the course material we're going to see. Okay, so so we're looking at least squares. So least square is part of what we called, if you remember the first lecture, it's part of sorry. So least square is part of so machine learning, of course, right? And it's part of supervised. It's a supervised method. Okay. So supervised method means that somehow we have access to some labeling. Okay, so we call that out of time labeling. So we have labels, we have access to ground truth. Sorry. Okay, so somehow we had access to a population of, to a data set where we had collected both the weights and the heights. Okay, and because we're trying to compute here the weights from the heights, the label here would be the weights. Okay, so we labeled, we had the access to the information, which was the heights, and we label it with the proper weights. Okay, and supervised here, because we have access to that, we have access to that information. So any supervised problem will start like this. Okay, so you collect a bunch of features that are basically scalar values, okay? And I will always note them x, okay? So there's a zoo of notations out there, okay? Because different communities worked on machine learning, okay? So statisticians, people doing AI, people doing engineering and so on, okay? I'm trying to stick here to the notations that are used in statistics because I found them very consistent and they're very helpful that we have the same notations all the time, okay? So these x1, x2, xp are the features you're going to collect, okay? So in our case, x1, for instance, was the height in centimeters, and x2, say, it could be something, for instance, you have the age, and say the last one could be as well some kind of categorical data. So maybe you have information about the person, so you know whether it's a female or a male, okay? And so that would be obviously some kind of classification problem at this point. But in the settings in that problem least squares, you can still use that kind of information because, for instance, you can say that female is 0 and male is 1, and you just plug these numbers in your equation and you'll be okay. All right, so just collect that information. So typically, you start from say a CSV file with a table, and each line corresponds to an observation, and for each observation you have a number of measures that have been made, okay? So in least square, you're looking at a linear model. And this is something that will be somehow confusing because we'll be working with somehow nonlinear entities, but this is something important. So here the quantity we're going to predict is going to be expressed as a linear combination of my inputs. Okay? So these x1, xp's, again, are your features. Okay, so this is your features. And this W1, WP, and even W0 would be the model parameters. And sometimes called the weights in machine learning, okay? So I'm going to stick to W as a notation for these model parameters. In statistics, this one will be called betas instead, okay? So instead of W0, W1, WP, they will have beta 0, beta 1, beta P, and so on, okay? All right, so it's pretty simple. We have a linear equation, so the outcome is a linear combination of our features. And the coefficients you have are, something that we want to find out, okay? All right. One special point, okay, in terms of naming convention, and it's a pretty annoying one, is this W0, okay? So in the deep learning community, they would call that the bias. All right, so they give it a special name, all right? So just something to be aware of, okay? All right, so other convention, I say that we have P features, okay? And that is not a mistake. We always use P, so the variable, the name P, okay, always corresponds to the number of features, okay? So every time I would say we have P features, okay? So if you start to say you have Q features, that's confusing everybody, and so you better use P so everybody agrees, okay, you have, large P problems, so that means we have lots of features, all right? So that's pretty much conventional at this point. So let's go a bit, so I'm going slowly here because actually it's quite deceptively confusing at some point, okay? So I just want to make sure that this is super clear. Last year I had people asking questions in week 5, and that's just because it didn't really follow that point very clearly. All right, so how does it work in your application? So obviously, this is a model for any given set of features and any given pair of x's and y. So in reality, what you do is you have a data set and that you collected observation from. So you have one particular observation, say outcome, and you will index it. Okay, so I index it 1 to say that's the first one, and I have my equation here, and now I will have to index my my features by the the data point entry. Okay, so it's here. I say here it's the first one, and I'm looking at the first feature or the first data point, and here we'll continue like this. Okay, so like so, and here I'm going to have n observations that and for which we want to fit the same model. Okay, so just to make sure, this n here, okay, that's index of the observations. So say in our case we looked at weights and heights, so we look at that for one person. So n will correspond to the number of persons we looked at, okay? And this is the first, so we have x, so x is your feature. Now we collect p features from n people, okay? So we have a matrix of these features, and we index that matrix by n and p, okay? So the first one, the first index here is the ID of data points. And the other one will be the ID of feature, okay? So again, n corresponds here to the number of observations or number of data points we have. It's always like that, okay? So we're talking, say, what is your n? My n is 10,000 because I have 10,000 pictures, all right? And p is maybe 300,000 because my picture is of size 300 by 100 pixels. So therefore, I have 300,000 pixels in my picture. Okay, so this is how it works. All right. Now, all right. So everybody is on board here. Okay. So so what happens? So we have these equations we want to fit, and of course, the problem we have is, life being life. This is never a real fit. So what you have is some kind of noise, okay? So, sorry. So you somehow kind of error or noise or however you want to call it. So you have a term here that explains, that says, well, actually, I don't really have this. This is not actually what the outcome is. I have a slightly different outcome because of X and Y reasons, but I don't know how to model that, so I just say it's epsilon, okay? And what we want to do somehow is to find, so the main thing with this game is like to say, right, we want to estimate this parameter, so these weights W's, in such a way that we're going to minimize the error, okay? So that's somehow what we want to do. We want to say we want to minimize the error. Now, here's a subtle point, okay, but a very important point. I mean, seems obvious maybe, but the error, there's no such a thing as the error, okay? Because we have n errors, okay? So when we say we want to minimize the error, really what we want to say is we want to minimize the errors, okay? Or the error terms. And the problem we have is basically what you have here is a vector of error, and you want to find, if you want to optimize for something, you want to minimize something over this vector. And the problem is that you cannot rank vectors, okay? So you cannot say one configuration of errors is better than another, okay? You don't have ranking in vectors, so you can't do that. So somehow you need to find a way of combining all these errors into one single number, okay? Because we know how to rank things over, we can say this error is bigger than this other if the error is just one scalar, okay? So we can say 10 is bigger than 5, that's easy. but I don't know with vectors, I don't know how to do that, okay? So that means that you need to make a choice on how you aggregate that error. And basically, what least square does is that it would say that the error, so I'll call that E, and it's a function of W, okay, would be the mean squared error, okay? And the mean squared error goes as follows. So it's the average over all my samples, observations, and of the prediction I make, okay? Minus I compare it to the actual outcome I observe, okay? And I square that. So again, this is my prediction. Okay, so given a list of these W's, okay? So sorry, this is a vector, okay? So this is my vector concatenating all my W's, okay? So I have some kind of error function that depends on these W's, and I check that my model fits, the prediction fits the actual outcome in each case, okay, the label. And so this is a mean square error. And this is the error that least square is going to minimize. Now, in machine learning, people, not in statistics, but in machine learning, people will call that as well the loss function. Okay? So we say the error function is, or the loss function is the mean square error. Okay? And sometimes this is called as well the L2 norm or whatever. Okay, so another way of saying that. So yes, question?
So are the epsilons just the errors?
So the epsilons is just the error term that, that shows the error between the prediction and the actual outcome. Yes. All right. So here, another way of saying that is this is the sum over all your errors terms squared, right? So nothing fancy here, but I just want to set the terminology. So this is the loss function for our machine learning system, which is least square, is the L2 loss function. Yes, question?
I always wondered, why do we use mean squared error rather than just say cube?
Right. That was my next point, okay? So this is what happens, okay? So you could say, I'll say like the loss function is pretty arbitrary, okay? We could have, we have somehow to aggregate all these errors in some meaningful way, okay? So you could have said, right, the error function here could have been, say, the mean absolute error or mean absolute difference, and in which case we would have written our loss function this way, okay? And this loss function actually is called, so you can say there, the mean absolute error or mean absolute difference as well, or L1, okay? So because we always want to do a bit more mathy, we don't just say mean absolute error, we just say L1, okay? It sounds better. So if you see in deep learning papers, they will say we use the L1 loss function, okay? So as it turns out, if you want to solve for that, this becomes quite nasty in terms of optimization, okay? And so not impossible to solve, okay? So there's been actually lots of work done in the last 10 years on convex optimization. And if you're doing a course on convex optimization, something you will see how to solve these kind of equations. But basically, you need an iterative technique. It's a bit slow, and you have problems with convergence. It's not an easy problem. It's a very interesting problem, I will come back to that. Has lots of very interesting properties. But the main point, what defines least square, is the fact you're using mean square error. If you're not using mean square error, you're not doing least square. You're doing something else. Okay? All right, so this is kind of like, I introduced you to feature vectors, talked about notations, P and N. I talked about the model parameters, and I talked about the loss function. Okay, so these kind of important points here that will come back. Yes, question?
Instead of using just squared errors, we can use any even powered errors, right? Because see, if you use an odd powered error, it's going to cancel out the negatives and the positives. But if you use any even powered, then it's not going to cancel out the errors, and then you can average over those errors.
So if you used other powers, so power 4, for instance, you can still solve for it, but then it's no more least square, and you will need an iterative system to solve for it as well. But I would say, so you need a different optimization strategy. Usually you don't want to go for higher powers, okay? So this is a bit of a digression, but if you look at what's happening in terms of the error, okay? So if you just look for one point, okay? So I'm just looking at here at 1 epsilon in all the errors I had, okay? So let's say it's epsilon I. Sorry, this is the value of epsilon I, and this is the resultant of the error you have, okay? So this is the error you have, for instance, this is a loss function you have associated. You see, it's a sum of, you combine all the errors for all the elements. So let's look at the L2 distance, okay? The L2 distance is just the parabola, and you have something like that, okay? And what happens when you do that means if you have a large error, okay, somehow it's called an outlier. Something that, you assume it's a linear function, but really in your population, in your data set, there is number of points. This model is just totally wrong. Something else is going on, okay? And for a small amount of your population, say, the error here will be arbitrarily large, okay? Because just the model doesn't make any sense for that. And what will happen is that for these points that are small number of points, the error might be here, and then you have a super large error. And your system is going to try to minimize for these points, but these points actually don't belong in your model, so they'll be causing problems, okay? So an example for that would be, say, trying to fit a line, and you have a cloud of points here, and then you have just one point here, okay? And this point clearly is just something else is going on here, okay? But if you look at least square, if we take this model, which is the perfect model, we're still trying to look at this distance here at the error between your prediction at this point and the actual data. And this error could be arbitrarily large, and by squaring, you're squaring that term, the error is going to become even worse, okay? And so that's going to have a super large impact on your loss function. And because you're trying to say, I want to minimize that, what will really happen is that as a result, what you will estimate will be more something like that. Okay, so you'll be pulled by this outlier. If you use a different loss function, so if you use the L1 loss function, so the L1 is just the absolute value here. You see here the contribution of a large point is important, but not as important. Okay, and so this is kind of a nice property that you kind of don't want points that are too far away from your model to overtake the loss function. So people are trying to go more and more towards a function that are called that are non-convex, and something like that. Okay. So a function like that, error function like that, would be interesting in the sense that if you have an outlier, it will have a bounded penalty on your loss function. Okay. So there's different names for this, like it's a whole family of different loss functions, different names. And if you look in save. So we'll be working with the Keras library for deep learning. There's a whole range of functions you can use to, depending on what you want to do, okay? L2, super easy to optimize, very nice convergence properties. L1, very interesting because of that singularity here, but kind of harder to converge. And these guys requires iterative techniques, and they'll be slower to converge as well. Okay, so sometimes it's better to start with L2 and just make sure that your data is fine. All right, so coming back on that, I'm going to skip the derivations, okay, because that's something you can look at home. But basically, I'm just going to point out this thing here, okay? To achieve that, it's the same technique we do all the time in physics, everywhere else. This, okay? We have this function of our parameters now are this model parameter we want to optimize for, and we have the error function, the loss function for that. To find the minimum, what we say is that we have to look at where the necessary condition for obtaining the minimum is that the gradient of that function according to the parameters is null, okay? Something you've seen in living cert and other place, you know, how you find the minimum of the parabola, where you can differentiate your parabola, and then you get, you know, because the gradient has to be null, okay? Maybe that's worth having a little explanation for that again. So let's say your loss function, if you plot your loss function, looks like this. This is, say, one parameter, and this is the loss function for that parameters. What we're saying here is that at the minimum here, the derivative is null. Okay, so we reach the minimum. On one side we go down, and the other side we go up. Okay, so we reach the minimum. All right, so in this case, the derivative is 0. Okay, that's in 1D, yes?
But that's going to be the case with maxima as well. You don't know.
It's true, right? Yes, it's true. But in the case of least square, it's fine because the only point that does that is the minimum.
It's in the case of a parabola, but you have a different loss function, then you can land up with a maxima.
So in the case of a non-convex function, loss function, then you can have multiple minima, and then just kind of be stuck in the minima, which is something we're going to see in the next handouts on logistic regression, so I'll cover that a bit more in detail. But the point here I wanted to make is that the derivative is null, but because you're working in with n dimensions, really what you say is that it's called the gradients, but you have the partial derivative for all the variables is null. Okay, so you look at the partial derivative for all the variables, and that must be null. You can look in the handouts. I advise strongly for you to redo these computations by hand. Very good exercise. But basically, when you rearrange everything, what you end up is something like that, a system of n equations. And I know there's a lot of squared and stuff like that, but still a linear system of linear equations in terms of the w's. So the x's are your features, and they are given, so they are constant. Okay, you're not going to change the features. That's what's given to you. So that's a constant. So all the terms in x squared and so on is something you can pre-compute or compute, and that still, you know, doesn't depend on your coefficients. So when you look at that, you have n equations of your weights, p plus 1 equation, and all the other terms that are not w's are constant for w. So you can solve for that, okay? All right. To finish this kind of painful part on notations, okay, I think this is important that we come back to the matrix notation because it's something I'm going to use all the time because I don't want to write W0 to WP all the time. I'll be using matrix notations. And I know some of you might not be super familiar with matrix notation, so I'm going to go slowly and just come back on one particular point that is important here. So this is how it works, okay? So I'm going to write, throughout all my slides, I'm going to write a scalar. So a scalar is just a 1D number, just one number, one real number. So as a x like this, cursive x if you want. A vector as a bold upright X and a matrix at the bold capital X. Okay. All right. So this is a convention I will have throughout my all the handouts you have. So that means that when you look at the list of all the outcomes you have, all the labels, you have this column vector of values that are collected. So this is a vector of y. I have this matrix here that we call the design matrix. And basically what the design matrix does, it stacks up all the observations you make about everybody. As well here we have the 1 and something I want to come back to as well. W is your vector of all your parameters, and epsilon in this case just all my observation. So now I can write my linear system as just this simple matrix equality if you want. So my vector of outcome y is the matrix multiplication of x, which is my design matrix, by the parameters, and there is this term which is the error term. Okay? Design matrix is a term that comes from statistics. Okay? So this is we always call it x. Okay? But again, capital X is design matrix all the time in all statistical papers. Let's come back for a second on our model, okay? And the reason why I'm going there is just because it's a bit of an annoyance you have, and that'll be true in all the other, in deep learning and everything else. Your model here has W0, and basically that's the offset we have, okay, or the bias, or whatever you want to call it. So we don't have to have that, okay? So sometimes some models, you don't want to have W0. You don't want to estimate for any offset. You just say your model is just W1x1 plus WPxp and so on, okay? So it's kind of an optional thing to have the W or not, okay? So one way I've done it, then after for the rest of the handouts, I've done it is to consider that when I say the vector of my feature vector, I'm trying to consider as well 1, okay? So I say W0 is the model, the coefficients that corresponds to a feature which happens to be 1, okay? It's kind of an artificial construct, but allows me to say that all my W's are the same thing, okay? They're all the same thing, they're all just my coefficients, and my features are my x1, xp, but as well 1, okay? And the 1 allows me to get me my offset. Does it make sense? All right? It's kind of an artificial thing, but what it allows me to do then is to do the maths in a bit nicer way. Means now I can say, for instance, that this scalar outcome is the scalar product of these two vectors, one being the feature vector and one being the parameter vector. And by having the 1 here, that allows me to get to that notation. Okay, so that's something you can see again and again in my slides. So maybe I'll just spend one more second on that. So I say that the outcome for the east observation is this vector, feature vector times W, okay? So if I expand what it is, that's transpose operations. That means that this would be a horizontal vector. So we have 1x1 xp, and W would be my W0, W1, WP. And this is a product of two vectors. And so this would be basically, if I multiply term by term, so 1 by W0 plus x1 times W1, and so on, okay? It's classic stuff, okay? And that corresponds to actually the equation I had for exactly my model, okay? So it just allows me, by doing this trick of putting the 1 as one feature, allows me to have directly that notation and being compatible with the offset or the bias. Again, this is not, maybe sometimes you don't want to have that 1, okay? So depending on your problem, you might not want to have that 1, and then just up to you not to have that in your equations. Okay, so matrix notations, I won't do that here. Okay, this is something that I want you to do at home. Basically, the notation here I have for the gradient is this notation here, and I derive some points about direct gradient computation from matrices. Now, you don't have to know that by heart. At the exam, that would be given as formulas at the back of the exam. But it's something to, it's not that hard to remember, okay? And to be able to do that allows you to go a bit further very quickly. This is an exercise I ask you to do as well, to compute the gradient of this, okay? So maybe not for tomorrow, but we'll see that on Monday, okay? So probably what we'll do on Monday morning is more like a tutorial type thing. So for people that are less familiar with linear algebra, I will just do kind of a bunch of exercises on linear algebra. If you're very comfortable with linear algebra, don't come, it's okay. But I'll go a bit more in detail in the derivations of matrix derivations and so on. All right, so when you do all these maths, okay, you end up with that, okay? So this is the same equation that we've seen before. So X is my design matrix as I've defined it before. And you have this equation, we call that normal equations. And it's a bit more compact than to have to deal with all these summations we had in slide 9. But basically, this is how you do it. And X transpose X, this is a square matrix of size P by plus 1, P plus 1 by P plus 1. So by the size of your parameter. And you can solve that using any kind of linear solver, very efficient, and you get there, all right? So going back to our original problem, I'm just going to do the first curve fitting, and then I'll leave that for tomorrow and more interesting bits. So we had that. In our case, we have to define what our model is. So we're going to use a very simple model. We just say that we have a fine model where the outcome y, so the weight, is some offset W0 plus a gain W1 times the height, which is x in our case, okay? So we only have one feature, which is the height of the people. Our design matrix is this matrix here, so we stack all the observations, and we have to use the 1 as well. Okay, we have to add the 1. You can plug that into the normal equations, so you can compute the x transpose x, and then x transpose y, and you have a 2 by 2 matrix and a 2 by 1 vector. And then you just have to solve for that equation using any kind of solver you find. Okay, so very easy to do. You can do that in Python, in MATLAB, anywhere. This is quite simple, straightforward to do. Okay. So in this case, when you run the inverse, well, this is what we get. So we get an estimate for the parameters, and so for the two coefficients, and then we can plug them in. And in our case, the bias or the offset is minus 99.5, and the coefficient for the weight for the height is 0.97. Okay, and that's our estimate for the model. Yes, question?
Regarding the exercise you had up on the slide and the tutorial exercises, are there any marks from the tutorial, or is it just kind of practice for the exam?
It's just like there's no marks. It's just doing things together, and kind of for you to going through the maths a bit to kind of reinforce that part. Because I know some of you don't necessarily have that strong background, so I think it's worth just spending 1 hour on the math notations, and just it's not going to be a tutorial about all linear algebra. I'm just going to focus on what's required for you to understand the rest of the lectures. All right.